Give me a second. I'll post a note on my office door so that people don't accidentally come and interrupt the lecture. All right, great. Let's get started. Uh, just as a reminder, we'll be continue to talk about the humble Gaussian distribution that we're so familiar with, but every time hopefully we'll learn something new, and not in this particular fashion portrayed in the XKCD. And yes, we will talk about confidence intervals in Gaussians, but the cut is of course vertical, not horizontal. Today right, this is an unusual session. I saw instead of sending everybody and myself to the far corner of campus and risk getting lost, we might just do this online. And next week we will be back to our usual room. Let me see. Okay, there's people still joining. The quiz is still on right now, and it will be closing automatically today noon. According to last year's statistics, people do pretty well on the quiz. So, right, if you're still hesitating, there's still time to do it. And I recommend doing the quiz rather than counting to redeem it using the final exam. And assignment 1 is out. I know there are lots of people have lots of questions. There will be a drop-in available this Friday at Ian Ross Graduate Teaching Room. So that's on the second floor of this building with a funny looking sculpture at the end. There's a question from Gandhi. If you meant the quiz, I remember it was meant to be due today noon. In case that's not correct, I'll double check. Let me know in the chat or through messages. If you meant the assignment, the due date is next week, Tuesday midnight, basically at the end of Tuesday. 23 hours, 59 minutes. I think that's the grayscale setting. Right. It's okay to ask messages just in the chat or unmute yourself and shout throughout the lecture. So today we will be talking about Gaussian processes. We'll motivate a bit and position this for you. The broad outline are basically we will start by reviewing linear regression, Bayesian linear regression again, and kernel regression. And then we will essentially be talking about two different views of Gaussian process. Basically, there are two ways to derive it. And hopefully, at least one of the ways work for you the first time around. And then we'll be talking about how we visualize Gaussian processes. This is an area with plenty of research and practice literature, and we'll talk a little bit about computation. So I expect, although I labeled it as first half, I expect this to take a bit more than an hour and a half because we'll be going through this slowly And the second half of Gaussian process content, I plan to give you a flavor about how to do classification and then use Laplace and refresh our memory on Laplace approximation that we mentioned in logistic regression, in Bayesian, when we cover Bayesian logistic regression. All right. So here's our Zubin's cube again. We will be going to this corner today. And as you can see, there are two ways of getting to this corner. One way is to introduce kernels from Bayesian linear regression that we visited and revisited a few times. The other way is to go from kernel regression and then make it Bayesian. So this first way is called the wave space view. The function space view is not necessarily going to this direction, but basically we will be looking at Gaussian process as kernelizing this verb, kernelizing Bayesian linear regression. And this will allow us to practice the kernel trick again that we saw last week, right? First, a word of motivation, right? Why do we need Gaussian processes? Here are three concrete examples. The first one is, how do we drive a robotic arm? You may say, hey, this is simple. Physics should tell us that. And this is in the domain of robotics. This is one of the simplest gadgets that you can see in operation. You have 7 joint positions, 7 joint velocities, and then accelerations. And then why the output is basically torques, how much force you should put on each joint in order to get the arm to do what you want it to do. Yes, you can solve it with physics, but the whole system becomes quite complex and also non-linear. We could actually just use machine learning to learn this complex function, right? The idea is we do not want to specify the form of the function, but we will ideally like to move this arm around, have measurements of these x and y's, and then use it to reason about where we want to move it next. Right, we want to compute the torque needed to move the arm along a given trajectory. And that will, of course, allow the arm to grab anything and transport anything that we need it to. Moreover, we will need not only the prediction, but also uncertainty. Why? Because in a robotic application like this, the physical system is imperfect. So there are noise involved in the measurement and also in the application of force. If we don't have uncertainty, we might be sending the arm into a wrong position without even knowing it. Right. So that's the first example from the Gaussian process book. And then the second example is to predict the yield of a chemical plant. Can you imagine you're producing some chemicals from raw materials, given the temperature, pressure, and amount of catalyst, and so on. This is also a fairly complex system. We don't know a functional form of y. And then we will also want full uncertainty estimate because this is a physical system. The last example is actually machine learning itself. Machine learning systems get pretty complex, as we have been hinting. So given any machine learning model or nuclear algorithm that we actually write and run, we need to instrument a lot of additional considerations in order to deploy it. For example, number of neurons, order of our, features for linear regression, regularization parameter. If we're using neural networks, number of layers, number of neurons, which activation function, and so on. So these high dimensional hyperparameters all influence the end result, basically the generalization performance. And this function itself is not known to have a linear form, right? What do we do? So there are basically two representation choices, two choices of functions. We've been talking about the first case up until like week 4. We restrict the class functions we consider, such as linear over a feature space. And then we could alternatively give prior probability to every possible functions. So last week in kernel regression, we have considered essentially kernel as a way to represent every possible function without pre-specifying what the feature is. And this week, we're going to say we're going to have a Bayesian view of this flexible function representation and work out how it works. So here are two more concrete examples. Similar to the chemical plant example, this is a paper written by a number of Australian colleagues about exploring Earth's resources, especially geothermal holes, drill holes in Australia over 10 years ago. So what's concerned here is the geological inversion problem. The input include temperature, conductivity, density, magnetic field, and permeability of the soil, and so on. And this is being formulated as a geophysical inversion, a machine learning problem. And this approach is based on Gaussian process regression. What does that mean? The output variable is the amount and properties of the geothermal activity in a particular drill hole. With a drill hole, you can collect lots of features, but you can't drill that much, as you can imagine. And this example is automl.org. So this has been a very active subfield in machine learning for the past 10 years or so, where one of the workhorses is to use Gaussian process to proactively figure out which set of hyperparameter to explore among the complex hyperparameter space. And it has evolved into not only its own subfield, it has books written about it. It has multiple benchmarks. For example, there's a related work called Neural Architecture Search, which explores the complex choices people have to make, machine learning scientists has to make when they try to use machine learning for some real world task. All right. Hopefully we've given you a flavor of what this might be used for. And then at the end, we'll come back and revisit the robotic arm application of Gaussian processes to ground this a little more. Let's start by reviewing linear regression as we know it. Right, so in linear regression, we have phi, the feature matrix that has n rows and d columns. And we have a target matrix of vectors. So in the Bishop book, it's called T, target, and now it's called Y. You might notice that today's set of slides has a different appearance as what we have been using before. This is evidence of basically different SML lectures building on each other over the years. So in particular, in 2023, the last time I taught Gaussian process was 2022, and in 2023, Yuan Sun Ting did a revamp of Gaussian process lecture, and we've been using that. It's pretty complete and nice. So there's also a slight change of notation, which I'll point out later on, which I think the reason for this is basically there are two renderings of Gaussian process. So in the in the PRML book, there's only covering of the functional view and not the wave space view. And then in the Gaussian process book, it has both. So this section of the wave space view. And this set of slides essentially unpacks the content in both books for you. And our hypothesis is, yes, you can go ahead and read those books. They are somewhat compressed for the level of the class that we're in right now. But hopefully with this set of slides, it does help. So we have D as the number of features and N as the number of training data points. In week 2, we looked at learning a regression function as simply the product of the feature vector and a weight vector, right? Phi x transpose W. And in the book, we've been referring to this as W transpose phi x, right? It's essentially the same as in the product are exchangeable. And then the optimal weight in the sense of least squares and also maximum likelihood can be computed analytically as essentially the inverse of a pseudo inverse of this matrix phi regularized with the identity matrix with this regularization parameter lambda. That has two meanings, regularization and then essentially Gaussian prior. Oh, I think there's a hidden boundary where I can't write it. Right, okay. So on W, the same thing. The pseudo inverse times the feature matrix and the target is the weight. And then you put this back and you get the prediction. And when we kernelize this, we still started from the same view of phi transpose W, although our goal was to get rid of phi and think in kernels. So when we use the kernel trick, what we can get is essentially a kernel vector of the new input data point or test data point, kx transpose times the regularized inverse of the kernel matrix in the training data times y is the prediction f of x. And this kernel k is what's called a gram matrix. It's required to be positive semi-definite, and every positive semi-definite matrix can be a kernel, and it's simply phi transpose. Notice that there's a difference between phi transpose, which is n by n matrix, and phi transpose phi, which is a d by d matrix. So why we would like to represent data not as features but as kernels, it takes the task out of specifying coming up with features and replace it with the task of specifying kernels. And if our feature is simply x itself, this is called a linear kernel. And if we simply square the linear kernel, we actually get not just the square terms of each feature, but we also get obtain the cross terms. And we walked through how to get this last week. And if we take the norm of the differences of these features, scale it, and then exponentiate, take the negative exponential of this, we end up with features of all orders of polynomials due to Taylor expansion. So here's another bit of review. Given that we've said, right, the analytical solution for weights is this, what do we, so what does it take to make this model Bayesian? And in particular, what it means to be Bayesian is to ask two questions. The first question is to solve for the posterior probability of the weight, rather than just one particular value of the weight. What we expect is that the posterior probability, when the noise and the observation are both Gaussian under Gaussian distributions, then the mean of the posterior distribution, so we expect E of W is essentially the maximum likelihood or maximum posterior mean. And we do so by essentially breaking down the likelihood or the posterior in two parts. One part is the likelihood for each data point with observation noise beta. The second part is the conjugate prior, which is nothing but Gaussian with the same regularization or prior probability. Right. This, oh, go back. Oh, E of W. Okay, where did the interesting is equal to W star. And then what we would want to solve for variance of W, right? So here we go. Right, so the posterior probability back in the Bishop book, it's written as M sub n and S sub n. And the reason for this is explicitly account for n number of training data points, right? And it essentially says the precision matrix or the inverse of the covariance matrix for the posterior of W is lambda D plus beta times phi transpose phi. And mu is beta times Sn phi transpose Y. So what we can see is that the covariance matrix for the observation, it shrinks, right? Because this is the inverse, it shrinks as we have more and more data. And the role of the prior also shrinks, which is replaced by more data if the phi matrix is bigger. What Bayesian linear regression means beyond just computing P posterior of weight vector is also predictive distribution. What does it mean? Given a new input X star, what is the distribution of Y rather than the value of Y, right? We have said that in the non-Bayesian case, it's phi transpose W, right? W star. This was the prediction. And we expect the mean of the predicted distribution to still be this. The question, which we know how to solve, the question is more like, hey, what is the uncertainty? In order to do this, we already know that the posterior probability of the weights is a Gaussian distribution with the mean and variance M sub n and S sub n in the Bishop book that we just looked at again. And this P of Y star given X star and W is also a Gaussian distribution. And what we are looking at is convolution of two Gaussians. And then we want to integrate out the weights. What that means is in the next slide, but let's review what we know. So we expect the mean of this Gaussian distribution to be nothing but mu transpose phi or phi transpose. And then there's variance term. From the Bishop book, we went through the derivation. The variance of the predicted distribution is 1 over beta, which corresponds to the observation noise, plus phi transpose sigma, the same S of n, S sub n term in Bishop's book, phi X star. So the second term is the uncertainty due to possible values of weights. The first term is observation noise that we cannot reduce. Right, you could intuitively think of the predictive uncertainty as two parts. One is observation noise that's built into the model. It's assumed to be Gaussian. And then the second term is, what if we have different W? And here's a picture to illustrate it. Right. So why do we want a full Bayesian treatment to begin with? Let's say we feed a linear model. In this case, features a linear y equal to W transpose X, right? Y star, a new point. And if we estimate W or the posterior distribution of W and then sample from it, we might have a line like this. It's a different slope. And we sample again, we get a slightly different line. And we can keep doing this. We'll get a few different lines. And we can see that given a new point, right? Let's say the three training points are illustrated on this diagram. And then given any new training point, we could have a few different values of y. And we can weigh the possibility of different y's by using the posterior probability of the weights. So that's. And this predictive distribution essentially integrates all possible weights. And hence it gives an uncertainty estimate. Right. Any questions about Bayesian linear regression and linear regression? Oh, here, go back. So taking another step, in last week, we have looked at essentially kernels. And what we talked about was called the primal and dual view of regression. In the primal view, we have parameters W with the optimal parameter. And the prediction is phi transpose W or W transpose phi. And the complexity or computational requirement for computing this is order of d cubed, basically the dimensionality of our feature vector phi plus d squared, right? Which accounts, the first part accounts for the inverse, the second part accounts for the matrix multiply. In a dual view, we essentially rewrite the weights as W equals to alpha n for each training point times phi n. Oh, go back. Right? The optimal alpha also involves a pseudo inverse, but in this particular case, it's an inverse of the n by n matrix. And the prediction is essentially also a weighted sum, but it is a weighted sum of weighted by alpha n and the inner product of each training feature vector and against the vector of the test point. We can also rewrite this as the kernel term between the test point and all the training points. So we write down, the goal of taking this one step further is to essentially write down the predictive distribution in the form of kernels, where the first kernel term is, this is, right, the big X stands for training data points in the training set. There is more than one. And the first X star point is one test point. All right. Any questions? So we kind of did this for the dual form, right? As you can see, there's the K matrix here. And then this is K of X star and big X in here. So if we succeed in doing that, that's a modest step. We essentially derived the Gaussian process with the weight space perspective. And if we stare at this predictive distribution a bit more, we can also set some expectations. So basically, if there were a set of feature vectors, we expect that the mean of the predicted distribution are still the mean of the weights transpose times phi of x star. The goal is to kernelize this, of course. And then the variance of the predicted distribution is similar to, right, we did this. We had this a few slides ago, phi transpose sigma or S of n phi, right? So the goal is to kernelize that. Right. So we start by doing exactly this. The mean of the predicted distribution here, we write it as phi transpose W. And then what we end up with is basically plugging in the expectation of W in the posterior distribution. So beta times lambda D plus beta phi transpose phi inverse phi transpose Y. The goal here is to replace phi with K. So from last week, if we use the kernel trick, we should be able to get, right? So this is D by D matrix phi transpose phi. We should be able to get from the inverse of the D by D matrix to an inverse of M by M matrix, which then gives us the kernel representation. Then phi star times the, we also would like to have the phi star together. We like to bring these two terms together in order to have the K x star x term. I think it's good to refresh our memory on this, so let's derive this. We're going to go to, again, this is a slightly new text stack, bear with me. Okay, so we'll just start a new notebook. Right. What we have, just to close to phi x star transpose W, or mean of W, and the quantity is lambda I of D dimensions plus beta phi transpose phi inverse phi transpose Y. And the kernel trick, what it does is essentially keep the first part fixed. Sheet. So copy this bit. And keep the last part fixed as well. and insert, the part we want and its inverse in the middle. And we do this by actually, let me correct this. So I think we will want, what we would like is to have this little phi with the big phi. So we want to put the big phi here in front and then insert lambda, the n-dimensional identity matrix plus beta phi transpose, which is where we're going. Since we insert an extra term, now let's just insert its inverse. Inverse, okay. So we have just made the expression, the linear algebra expression even longer, you said. Oh, what did we actually do? Not much. And our goal is to actually remember what we're going is we want to actually keep this term. And then ideally have these two terms cancel out. Then we are kind of done. We're done with the n by n kernel matrix. So the way we do this is to, okay, the first term is still stays as is. We can move beta to the front. And then the second term stays as is. And then we can combine these two terms in the middle by multiplying phi transpose. So lambda phi transpose I of n is phi transpose plus beta phi transpose phi transpose. And then the last two terms stay as is, lambda I n beta. And now you probably know that we should work on this term. What happened is, now that we can see essentially phi transpose is on the right-hand side of both expressions, we can actually take it out on the right-hand side. What that means is we copy the front part. Stays fixed. Be smaller. And then the next part is essentially what we want to do is to take phi transpose out from the right-hand side. Once we have taken this out, the second term becomes phi transpose phi. And notice that this term is d by d. Therefore, the first term is d by d. What we have done is to use essentially left multiply on the n by n matrix and then of the identity matrix and take it out on the right-hand side. That turns the first term into d by d matrix. And the last term stays as is. Inverse y. As we can see, these two terms essentially cancel out. They are, the first term is the inverse of the second term, right? What we're left with is beta phi transpose x star big phi transpose lambda n plus beta phi transpose inverse y. And as you can spot it, the first two, the vector matrix product is kernel of x star with respect to the training set. That's a kernel vector. And lambda I n plus beta kernel k x x. Some books write out what the kernel matrix is taken over. I think the GP book does. The Bishop book doesn't. And y is a vector. So now we've essentially achieved what we wanted. Get rid of all the phi's and then represent this expression in kernels. And this is called the kernel trick. And I hope it helps to walk through it and then essentially refresh our memory. There is a question on chat. Okay. Right, okay. Julian actually sent the chat to everyone. Let me address this. Number one, is there a high-level standardization in the symbols and notations across different fields that use SML? Good question. The short answer is no. The reason we stuck with essentially the one set of notation used in the PRML book is that sticking with the same set of notation helps us understand things. And I also feel that this is perhaps the right time for us to start being exposed to the variation of notations. Moreover, whenever we read a research paper, it should have one consistent set of definition of notations. Actually, so what notation works best? Besides the superficial choices of which letter or Greek letter or Latin alphabet to use for each quantity, the suitable choices of notation depend very much on the concept being represented and which novel concept is being invented for each paper. So for example, trivial choices such as X star and sometimes how we label the training data. When it's a time series, then you need to think about, hey, where did you load the time index? Wrong choices can lead to clutter notations that actually confuse your readers, but the correct choice helps understanding. The bad news is, of course, we will need to reorient ourselves on the particular notation any given presentation uses. For this particular Gaussian process lecture, we aim to help by essentially keeping an eye on the notation of both the PRML book and the Gaussian process book for reasons we talked about. At the end of this slide, if you downloaded it and if you fast forward, there's a table of the contrast of notations between these two books. The same quantity, here's the different ways that it's represented. Right, number two, if yes, is there a website or easy reference that you can recommend which has all the symbols we encountered in SML in this class and beyond? Good question. I believe, let me do a real-time check. I believe the PRML book does have a notation table. Right, okay, it does have a note about mathematical notations in the prefix, right? So, but the answer in general is no. You have to get it out of whichever literature you're trying to consume. I'm sorry, this is not super easy. For example, at least in both the SML, PRML book and the Gaussian process, the input is called X, the output is called Y. Sometimes we have input called U and the output is called X. So we need to be careful. And at least across the two books, also the convention for vectors are the same. That cannot be said. That's kind of not true in general. All right. Okay. Thanks, Julian, for the question. Let's move on. So we just covered the kernel trick. What's more is that we can remember kernel are just positive semi-definite matrices. We can essentially absorb the constant beta into the kernel term, right? So you can imagine we pretend that we make a new feature that's square root of beta times each of the old feature, then we essentially absorb one constant term, the extra constant term in the kernel, so that we don't have one more symbol to look at. And this is also part of the notation game, where if you denote the kernel with the constant inside, then we have less to keep track of in our head later on. Ooh, right. And what is the predictive variance? In the Bayesian linear regression lecture, we said it is this. Now we would like to rewrite it in kernel terms. Notice that this has broken down with 3 terms. The first term is the same 1 over beta. We actually have an extra expression because of the kernel of the test feature, basically the inner product of the test point feature with itself. Right. Notice that we said the kernel is simply a similarity metric between 2 high-dimensional feature vector. So the similarity or the inner product of any point with respect to itself is not a fixed value. So this is more or less a calibration term. But more interestingly, the third term here is essentially the kernel vector between the test point and all the training points, basically inner product of this giant kernel vector, which we can sort of as, right, is a vector like phi of x star transpose and phi x1. And you do this for phi of x2 all the way to phi of x star, the inner product of phi of xn. Okay, this is a big vector. So the third term is essentially the inner product of this big vector with itself. This is the transpose version of it. Modular, essentially, they're modulated by the kernel matrix of the training set. Inverse, right? Right, so it's the inverse of the kernel matrix or the Mahalanobis distance induced by the kernel matrix. And note there's a subtract sign in here. So basically we calibrate the kernel value of the test point with respect to itself with this Mahalanobis distance of the kernel vector of the test point. Okay, so what did we just do? We spend a lot of time reviewing linear regression and Bayesian linear regression, right? We said that the predicted distribution is this Gaussian distribution, where the mean is the optimal, mean for the optimal weight is the follow. following, and the variance is 1 over beta times this x plus this extra term. We kernelized it using the kernel trick, where the mean of the predictive distribution. So notice that this notation, go back. Oh, I think, right, okay, let's go back. So this particular notation is actually mean or of y star as a function of x star. And the function part refers in particular to the first term, where the first term depend on x star, but the second term onwards only depend on the training data, right? So this is training data. Can be pre-computed. So whenever we want to compute this, we can pre-compute the later part and then plug in the first part about the training data. What this means that this two red boxes on the left are the same. It involves inverse of an n by n matrix. We'll talk about how to compute this somewhat efficiently, or as efficiently as we could later on. So these expressions are equivalent or were in the Bishop book, except they were derived differently. We'll go back to the other way of derivation later on. Okay, so it's time to do a poll. Given that we have, let me see. Okay. Let me juggle with my tech. I will open the poll. Okay, there is a question open now with 3 options rather than 4. Go into it and present. And for that, I will need to unshare. Okay, can allow multiple presenters to share. Let's see what happens. Okay, you can start responding. Hopefully you're seeing the poll screen. No one? Oh, the quiz is not visible. Activate. Okay. I've clicked on the activate button. Hopefully it works. All right, our first response. Thanks. I'm curious whether you can see your own response right now. I hope you can. All right, I think the options are more or less converging. Oh, still going. Cool. Can go back and look at the different options. Cool. All right. Okay, the option A says that the Gaussian process regression can be derived using the kernel trick. On the results of Bayesian linear regression, that is correct, and that's how we have done this. The kernel trick involves matrix manipulations. I probably should strike out advanced too. It's basically matrix manipulations in order to convert a D by D matrix into N by N, N1. So using this kernel trick frees us from deciding what a feature vector is for a problem, but we have to think about what is a kernel instead, and we'll see some visualizations about it. And then the variance of any point is still larger than 1 over beta because we essentially have not changed the model. So let's look at one more view of Gaussian process before we move on to some visualizations and talk about computation. So how do we more tightly connect kernel regression and Gaussian process in the Bayesian view? We do this by essentially look at multivariate Gaussians. So let's call it n+1 dimensional normal distributions. Because we've looked at it for a fair bit when we were looking at Bayesian linear regression. This is called the functional space view. So a Gaussian process, we can think of it as a probability distribution over functions. Therefore, it's called a function space view. If you haven't, most of you probably haven't taken functional analysis in terms of thinking about functions as variables and distributions of functions. Don't panic. So despite the notation, you can understand this section without knowledge of functional analysis. So we think about the probability of the different functions. And in here, a shortcut for these function values is you can think of them as y's, y1 through yn is a normal distribution. Moreover, we also take the liberty to set all of the means of these functions to 0 because we don't have prior knowledge, and we can also shift a function to having a mean of 0, right? And therefore, we can concentrate our attention to their covariance function. And you will be like, oh, okay, so what is a covariance function? So again, we simplify our mental representation of these as essentially a m+1 or m-dimensional Gaussian. And then their covariance function is nothing but the covariance matrix or kernel. How does this work? Bear with us for a few more spots and we'll see. So the notation, again, in the Gaussian process book, and not so much in the PRML book, despite the Bishop book actually uses this particular way to derive the Gaussian process, is the Gaussian process notation is that it's a normal distribution of functions with 0 mean. This is a m/1 vector of zeros, lots of zeros, and the kernel matrix is m/n. Okay, taking this view, right? Let's see where we get. So The top is the expression we just looked at. And you might say, hey, we assume there's a long vector or a function that has mean 0 and covariance k. But is there essentially no constraint on k, besides that it's positive semi-definite because it needs to be a valid covariance matrix? Actually, the underlying assumption remains the same. We assume the function is a matrix vector product between the underlying feature that defines the similarity and the weight vector. If we don't impose much further information, so basically this feature and the weight vector decides what the kernel similarity, the covariance structure is, right? So there is still an underlying coupling between how we think about similarity in feature and kernels. Except in here, we think directly about this n-dimensional joint distribution of the y's given a whole set of x's, right? And we assume that the prior of the weights is a broad, right, a Gaussian prior with 0 weights and covariance alpha, like independent covariance, right, of alpha 1 over alpha times the d-dimensional identity matrix. If we assume this, then the mean of y is 0. So basically what we wrote above does not conflict with the prior on weights. And the kernel matrix is essentially expectation of YY transpose. So YY transpose is a long vector taking an inner product with itself. It is basically a matrix of n by n, right? And we can see that, hey, if we expand on this again, feature times weights view, we get the expectation of the weight vector with itself, which is 1 over alpha times IFD, and then phi comes out. Therefore, we get 1 over alpha times the phi kernel matrix as we have defined it. So this is how the underlying machinery works. Now, we now know that we should concentrate our attention on the second order statistic or the kernel matrix, kernel structure. And if we look at the joint probability between essentially the training point, training targets, and the one test point, then this kernel matrix becomes n+1 dimensional. And this is what the Bishop book uses. And it is assumed in the Bishop book that the kernel value of in this big matrix for two different given inputs m and n is 1 over beta plus the original kernel value. This is still right, and this is the exact equation back in the Bishop book. So the kernel matrix constructed this way is still a valid kernel matrix or still positive semi-definite. And you can show it using the kernel properties we covered last week. So what's the big deal of this? It basically allows us to deal with infinite dimensional functional space. So basically, functions f of x. It's hard to think about functions, probability over functions, right? We convert this into thinking about probability of y vectors. So we essentially study a finite distribution of any n plus 1 points in this XY two-pole space, right? And this is our way around thinking about functionals in a more rigorous or mathematical sense. So practically, we essentially convert this to thinking about like, and this is a multidimensional Gaussian, right? That we already know how to think about. So let's look at a picture, and we'll look at more pictures later on. So this is one pictorial view that will appear a lot when we look at Gaussian processes. So prior of y is the function with zero mean. Zero is a current vector. A prior of a zero mean function, where the mean is here. You can see if we sample, in this case, 3 instances of this function, with the same covariance function, we can see that we get different functions in this space. They are continuous, right? And what we would want to reason about, right, or the goal of this functional view is to think effectively about P of y, right, given x star and x, xy pair in the training set. And this is defined with the kernel. And how do we draw, right? So as you can see, if once we see 1, 2, 3, 4, 5 training points, posterior given training points, what we have essentially plotted here is essentially y's, okay. What we plotted here is x star belong to some set from -5 to +5. Like if you're doing Python, it will be linear spacing between -5 and +5, and a step size of 0.05, let's call 0.01, whichever step size you choose. Basically, for every single for a set of evenly spaced point on the x-axis, we compute P of y star. And we can see that the uncertainty shrinks towards when we're on the training points, any sort of uncertainty becomes bigger between the training points. Right, so as you can see, the uncertainty cloud here is bigger. We'll define what exactly this is in a bit later. Right, and what happens between this prior distribution and this posterior distribution giving 5 training points is that instead of assuming all different shapes, now the posterior is concentrated on one particular set of shapes, right? It's rejecting functions that do not satisfy what the training point, right? That do not support that the training points are observed with high probability or already observed. So in this case, it's probably these functions in the posterior are probably simplest to this purple set of functions and not so similar to this red instance of yellow instance of the functions. So again, what we have looked at is this joint prior distribution of the training points y and prediction point y star. And what we want to compute is the conditional. So we know the joint, and then we want to compute a conditional of y star condition on y. So this is what's essentially a one-dimensional Gaussian condition on n-dimensional inputs, right? And you know what? We know how to do this. From the prerequisite section covered in the Bayesian linear regression lecture in Bishop PRML chapter 2, we know that if we partition the Gaussian into two parts, right, essentially the covariance matrix, where is my, okay, is partitioned into covariance of the A part, covariance of the B part, and then we can express the conditional mean and covariance as an expression of the original partitioned mean and covariance. So we want to essentially use these to compute the downstairs. So the mean is right. Let's look at this, the covariance part first, which is sigma AA, which is the upper left-hand corner of the covariance, 1 of beta, that's the observation noise, and also the kernel structure of the test point itself. In here, we will be partitioning this by doing essentially y star first and then y as our vector partitioning, and then subtracting sigma AB, that's essentially the kernel vector of the new point with respect to the training points, and sigma BA at the end, which is the transpose of this. It's the same thing. And then the kernel matrix plus observation noise inverse. Right. So it may look a bit abstract at the get-go, but thinking about it, once we adopt this, the function distribution is nothing but an n-dimensional Gaussian condition on the training points. Then the observation covariance is a simple application of this conditional Gaussian formula above. Right. You may say, hey, what about the mean, right? So oh, there's a typo, this is beta. Right, and the conditional mean is the original mean. So this mu of x star itself, or mu of, sorry, y star, y self is 0 based on this assumption that all of the functions have 0 mean. And then what we need to look at is simply the second term. Right, and mu of b is also, this is also 0. Because all the y's are 0, what we are left with is essentially 3 terms. The cross variance of the two training and test points, and also the regularized kernel values of the training points, followed by y. Basically, the observed values, despite the mean expectation is 0, but the observed values will have its own values. Okay, what have we just talked about? As you can see, if you go to the Bishop book, it has this simple illustration of essentially a two-dimensional visualization where T1 is the training data point. And now we would like to compute P of T2 given T1, right? So the covariance structure of T1 and T2 are assumed to have this red elliptical contour. And once we condition on T1, the mean of X2 shifts, right? Because they're positively correlated, T1 is to the right-hand side of the mean, and then T2 is also larger than its mean. That makes sense. And the variance of T2, conditional variance of T2 also shrunk from what it was because conditioning always reduces uncertainty. That's another, so rule of thumb in information theory. So let's look at, well, this is our opportunity to look at visualizations of Gaussian processes more systematically. Here's a PDF to explain it. Let's see. Let me bring up that visualization file and think it'll be good to look at it together. Here we go. Right, this visualization is developed by Tanbui, last year's lecturer. And I think it's really walks through what happens in these Gaussian process visualizations in a way that helps you. Oh, where's our full screen view? I believe you can see the visualization. Give me a thumbs up if you can. If you're seeing a circle on two concentric circles on screen, give a shout out in chat or just unmute yourself if you can, if there's some bug in this. So let's go, right? So we know how to draw two-dimensional Gaussian visual distributions. These are informative, but often not enough. So let's walk through how we go from the two-dimensional drawing to visualizing n-dimensional Gaussian distributions, aka Gaussian process, right? So here is two independent or uncorrelated Gaussian variables, y1 and y2. The covariance matrix is shown on as identity matrix. You can see my cursor, you can probably see this, right? And then now we have introduced a little bit of correlation between the two variables. As you can see, the covariance contour got a bit elliptical, and then we keep going. There's more and more correlations. So the idea for Gaussian process, the kernel matrix, is to introduce correlations. Basically, it wants nearby points to be close in a high-dimensional sense. So, okay, even more correlation. 0.7 now, the covariance between the two dimensions 0.7, so this is fairly elliptical, or 0.9, right? And now we sample, if we sample lots of points from it, this is what we expect to get. And when we condition on y1 equal to 1, this is the blue curve shows the conditional distribution of y2 given y1. And the expression above is simply what we looked at in the other, in our textbook about the conditional. You can compute these in analytical form in this particular conditional distribution. And if we draw from the conditional distribution, basically draw different values of y2 given y1 equal to 1, these blue points are what we expect to get. Okay. So far, nothing new, still two-dimensional Gaussians. Okay. Page down. Right, so if we have a slightly different covariance structure at, let's say, 0.7, then the distribution is a bit wider. It's larger conditional variance. We can basically relax the cross correlation, and we can see the conditional become wider and wider until when they're uncorrelated marginal distribution. Conditional distribution is same as the marginal, but otherwise conditioning does shrink the conditional covariance, right? So how do we go from this to visualizing a high dimensional distribution. So on the left-hand side is the picture with a 0.9 cross covariance that we were looking at. And we essentially put the variable index y1 and y2 now as the x-axis. So given the sample point, what this means is essentially y1 equals to about 1.5, and y2 equals to about slightly more than 1.5. They're highly correlated, so these values tend to be quite similar. So each point is converted to a line in this space, right? So far, we still haven't done anything new. And if we draw a different point, it corresponds to a different line. You can see they are still quite highly correlated. Therefore, the line tend to be flat rather than having a steep slope. Okay, we keep drawing and the line moves, right? Keep doing this, and it could be at the bottom, right? Nothing, so the line keep moving. And the conditional distribution of y2 given y1 is that now instead of drawing the two coordinates of the line, we fix one coordinate to be this red dot, and then we draw where the second coordinate is according to the blue distribution that we looked at. So that will be the blue dot. And if we fix the first point, then essentially the blue dot oscillates up and down from the red dot, and we expect it to not essentially deviate from the value of the red dot too much, right? Because of the high correlation. So this is how we visualize, wait. Essentially still a two-dimensional Gaussian in a somewhat silly way. But this allows us to look at multi-dimensional Gaussians. We can't really draw a multi-dimensional mountain, right? So assume now we have a 6-dimensional Gaussian with the following covariance matrix. So you can imagine, you can see that this covariance matrix has a structure that, can I draw on this? Where's the annotate button? Yes. So the self-correlation is 1, and then nearby points have covariance or correlation 0.8, and then 2 step out it's 0.4, and 3 step out is 1. Right, so you can imagine this kind of covariance structure makes the function somewhat smooth. Oh, 22, okay. So I can draw. So in here, if we just look at the covariance between y1 and y2, the off-diagonal term is 0.8, slightly less than 0.9 as we were looking at. And then we can essentially draw all 6 points and then visualize them as a line. And you can see this line tend to be somewhat smooth, right? Oh, and sometimes not so smooth because of it allows larger jumps, right? And then if 1 step allows larger jumps, then over 3 steps, we can have a jump from the top of the range to the low end of the dynamic range. Notice that all of these points still have 0 mean as prior. So this is how we visualize a multidimensional Gaussian, right? And we can keep doing this until so you might say, how does this help us, right? We're just still playing with multidimensional Gaussians. So here is the thing, right? We can fix a subset of these variable indexes, which are our training points, namely these red points. And this will allow us to ask questions about these blue points that are conditioned on these red points. As we know, the blue points follow a conditional Gaussian, and we can sample them, right? So given the 3 fixed red point, we can see that the function value and the blue point can be at different places. So you may ask, how do we sample continuous functions, so to speak, right? And when we actually plot Gaussian processes, we actually do this, except the variable index is much finer. It looks like it's continuous, but in Python, you plot the continuous function by essentially sampling or do regular grading on the x-axis. And this is what the resulting function is like. And you may say, right, so these are the different samples of the resulting conditional function. What about uncertainty and what is the mean? So as we talked about in the lecture, we can compute the mean and variance. And what does this allow us to do? Right. So we can actually plot the mean rather than each sample as a blue point. And then we can have this essentially confidence interval or error bound. As we know, in Gaussian distributions, so the error bar is 2 times the standard deviation. So, all right, I have to draw with not so good at drawing with my mouse, I guess. 2 sigma means essentially it's a 95% of the probability mass in this conditional Gaussian distribution lies within 2 sigma on each end. Right, and this is the plot that we're seeing, right? So essentially, for the training points, we already observe them. Then for each test point, we draw its mean and 2 sigma. Okay, next plot. We can sample from more than 6 points, and that will give us a continuous looking line. Let me clear out the drawing. Does not help this. Right, if we sample from the prior, we get this. We essentially get a 20-dimensional function that looks rather smooth right now. And if we have 3 training points that are fixed on the left-hand side, we can see how the rest of the blue points wiggle with this kind of covariance structure. Remember, right, we'll take a look at the kernel function later on, but essentially a lot of kernel functions enforces that nearby points are close by. Therefore, the resulting function is somewhat smooth. And then if we accumulate all of the samples we get in the last few pages, or if we compute the mean and variance of each sample point, we essentially get this plot where the mean is expected to be this, variance is denoted by the blue bar. We can also say, why does our training point have to be on the left-hand side? Extrapolating on functions don't work so well, right? As we know, we can fix a training point on near the right-hand side, or we can actually proactively acquire an example, such as by running a lab experiment closer to the right-hand side, in order to reduce the uncertainty on these function estimates. And look, it indeed does, right? It reduces the uncertainty somewhat close to it, but far away from it, the error bar still grew. So, and more training points. So from here on, we can see, hey, maybe let's acquire another observation in the middle. And this is essentially the picture like this is how we see Gaussian process regression plots drawn. Okay, let me stop sharing and show you some other, or actually this is a good point to show the SML book visualizations. So stop sharing this one, but let me start sharing this one. Right. So, and this is what we just talked about in animation form. If we sample from a prior of a square exponential kernel, and we can also adjust, for example, the kernel, if the sigma value. Well, actually, if we adjust the length, it will become more or less wiggly. And we can also add another sample to be 4 samples. We can click on this interactive plot to introduce training data points. Say I have a training data points here, and further down here, then it will essentially control the different samples. Like I can stop the samples from wiggling, which essentially says if I would like to do a conditional sample of these functions, these 4 curves, maybe I'll delete one, 3 is easier to see, maybe 2 is even easier. These 2 curves is what I get for as samples, but then these shades are the 95% confidence intervals that you often see plotted in Gaussian process results, right? What we essentially do is to go through the grid points in here from -25 to +2, and then plot the confidence plot and connect the upper and lower envelope of these confidence intervals that gets us these shades. And the dashed line is, of course, the mean of the function. And you can play with different kernels, right? Say if we do a different kernel, rational quadratic is also somewhat smooth. And different kernel choices does influence the mean and variance of the function we end up estimating, right? For example, if we adjust this scale parameter L to be very large, then the function varies slowly. And if we adjust it to be small, then it sort of varies more quickly. So these are how the visualizations of Gaussian process come about. Okay, I'll stop sharing this. Now you know where this picture comes from. And the mean, and you also know how to compute the mean and variance at any given input point, right? And if you repeat it over a grid of input points X, you get this picture, right? And if we reason about the different terms that influence the mean and variance at each point, so the influence to the mean depend on the proximity of the test point to any training point. And intuitively, it's most influenced by the nearby training point and less influenced by the faraway training point. And the uncertainty reduces given the training data. And it does not depend on y, curiously. So basically, the uncertainty does not depend on where the y-axis of these training points. They only depend on x, and that is somewhat curious. Moreover, you might ask, what if my input is not one-dimensional? All the visualizations we have looked at so far is actually with the input one-dimensional. With 2 or higher dimensions, we are still left with the challenge of visualizing high-dimensional functions, right? So in 2D, we essentially have something like this, a landscape of x1, x2, 2-dimensional input, and then y goes on the y-axis. You can imagine not just a mountain, but a landscape of many mountains and valleys and dips. Maybe it's more similar to the seafloor as the closest visualization. Oh, right. Ooh, my iPad has just gone dark. I wonder what happens. Sorry about that. Any questions so far? Oh, right. So the iPad is just rebooting itself. We'll wait for it to come back and dial back in, but this might be a good opportunity to pause and take questions before we talk about computing Gaussian process. Curious how. Nope, no questions. So that means everyone understand what we're talking about pretty perfectly. Let me just get back online. Okay, wait. Why is it's trying to
Recording in progress.
okay, excellent. Still a question. Yes, thanks for the comment, Julian. Yes, please feel free to play with the visualizations. It does take a lot of energy to make them, and it's good that the community have so much to share in terms of helping others understand what the machine learning model actually does. And as you can see, Gaussian process is quite a popular tool and well-researched tool, so much so that there are many visualizations and also an entire book written about it. Okay, let's get back to what we're gonna cover. There we go. Yes, so let's try and understand this kernel a little more. Let's say we have a kernel. This is a figure in a Bishop book. This kernel has a number of parameters. There's theta 0, theta 1 inside the exponential, theta 2 as a constant, and theta 3. Now you wonder how each of these parameters influence the shape of the function. So these functions are all 5 different samples from the Gaussian process prior, right? So our default can be that theta 0 is 1, theta 1 is 4, and then theta 2 and theta 3 are zeros, right? So this is the basis of comparison. So if we increase theta 0, that basically makes this whole expression larger. The similarity become larger. And the theta 0 is being increased to 9 from 1, so 9-fold. And you look at these 5 samples drawn from the same random seed, actually the functional shape did not change much. You know why? Because the linear term in front of the exponential term, the effect is still overwhelmed by the exponential square, negative square exponential term, right? So therefore, it's most important, right? The effect will be most important if visible if we adjust the scale parameter inside the square exponential term. And that's what we're gonna do in the next one, where if we increase theta 1 from 4 to 64, what this will do is, if we imagine this being like the width of the Gaussian or the bell curve, it decreases the shape of the bell curve, right? Square root of theta 1. Square root of 1 over theta 1 is sort of from 1 over 2 to 1 over 8. That decreased the width of the bell curve by 4 times, where therefore the function becomes sampled prior function becomes a lot more wiggly. Now, what about, right, if we decrease theta 1, because it's sort of such a sensitive parameter from 4 to 0.25, then this sample function become a lot smooth varying and basically changes slowly. It enforces larger similarity across larger length scales. Now, if we add a constant term, theta 2, we change theta 2 from 0 now to 10, what happens with all the rest of the terms fixed? You can see that the dynamic range of these functions sort of decreased. Why? Because unlike theta 0, which multiplies this exponential term, theta 2 essentially forces the kernel value to be no less than 10 to start with. And what happens is that it forces the function to be value-wise very similar. Therefore, whenever if we sample from, say, left to right, then whenever the first point end up with, then the rest of the function is forced to slowly vary along the initial point, right? So the way we sample the prior distribution is not by sampling, let's say, 100 points of X simultaneously. We sample one of these points and then condition the second point on the first one, condition the third point on the first two, and so on. Right, and this is what happens. Finally, we keep the rest fixed and vary theta 3 on the linear term. We know that for polynomial kernels, it tends to vary widely, or basically it tends to go unconstrained, like polynomial feature functions on either end. And this is what happens here too. So it still gives higher similarity values than the default, which is this one, but then it modulates in a different way. Right. This page also points to the similar animation we just played with, so feel free to have a go. And this was the page we already looked at. So now let's switch gears. So before we go on, are there any comments or questions about Gaussian process computation, like representing Gaussian process in a function view or visualizations? If not, so here's a recap of how we computed Gaussian process. Essentially, in the both weight space view and the functional space view, what we have concentrated, the new quantity is really the predictive distribution. Condition on all the known points, right? And as we saw, the bottleneck for computing this is this matrix, n by n matrix inverse term. It is generally order of n cubed. And we compute this by what's called the Cholesky decomposition of this matrix, this regularized kernel matrix. What the Cholesky decomposition is, again, you can dig deep on this piece of linear algebra if you want to, but it also suffices to know that a Cholesky decomposition is simply the decomposition of a positive semi-definite matrix into two parts, where each part is this lower triangular matrix. What does that mean? As you might remember, L matrix look like this. So the top triangular part is all zeros. And then the lower triangular part is non-zero. So there are numbers filled in here. This is L. And then L transpose is, of course, if we transpose that, we're going to get 0 on the lower triangular. And then we just copy the numbers. It's the same numbers on the top half. You might say, why bother, right? So it actually reduces. Come to think about it, right? So K is symmetric when K is a proper gram matrix. So K is symmetric. That means there is only essentially n choose 2, like degree of freedom, right? Therefore, the Cholesky decomposition with the lower triangular matrix also have the same number of essentially free invariant entries. So we can do this without sacrificing the representation power of K. That's nice. And we claim that the Cholesky factorization is n cubed over 3 operations. You don't need to know why. You can take this as given or trust us. Because it is well known, or people have spent the last few decades trying to speed up matrix decompositions, and there is a garden variety of them. What we're talking about is Cholesky factorization, a full matrix A equal to R transpose R, where, yeah, and it's n cubed over 3. We might have seen, right, there's different ones, such as LU decomposition. There is SVD or PCA, as we will cover next week, or remind yourself from IML. If we compute, right, for SVD for non-square matrices or PCA for square matrices, it's actually more expensive than doing a Cholesky factorization. We know that if we want essentially K plus lambda inverse, we can always do an eigenvalue and then inverse the eigenvalues, inverse each eigenvalue, and then put the matrix back together, then we get the inverse. But that's not the fastest way. So as we can see, SVD or PCA, it takes more than 1 over 3 n cubed. So in this case, the overall complexity is still in the same complexity class of order n cubed, but it is the constant in front still matters. As we can see, for the same n, we will get an order of magnitude speed up, right? If we just do 8 times n cubed over 3, that's about 24 times difference. Therefore, we choose Cholesky. And you will say that, hey, then what? Once we have done the Cholesky decomposition of this regularized kernel matrix, we compute another intermediate variable, right? So what Cholesky allows us to do is when we try to compute the linear system AX plus equals to B, we have this right divide operator in both NumPy and linear algebra, right? X equal to essentially A right divide B. We do this, we compute the intermediate variable as alpha as this L matrix, right divide Y, and then the L transpose right divide the result of that. The claim is the mean estimate of at any new given point, or alternatively, if we're computing this for a whole set of x coordinates, we can essentially compute the kernel vector or matrix on these new points, and then matrix multiply alpha as the vector we obtained through this. Right, so Cholesky times y is what this alpha vector represents. Now we still need to compute the variance term. And to compute the variance term, we have the kernel at the kernel value at the test point. So that's given. And then what we need is this another new vector called v. Basically, it is half of this inverse, right? So we can think of this as half of this is essentially kernel of the new point against this times L. I put that in quotes because we're Cholesky decomposing the inside part. We need to essentially compute the inverse of that. Therefore, that leads to the right divide operation of L with respect to this kernel vector. And then the other half is essentially the same thing, transpose. So that leads to the V transpose V part. So we have said that for square exponential kernels, also known as Gaussian kernels, that this scale parameter is quite important, right? Basically, smaller scale, well, we need to pay attention to whenever this scale parameter is presented to us, whether it's on the top or the bottom of this square fraction of its square exponential term. So when in this slide, when the L is small, it varies quickly. When L is large, it varies slowly. Note that L in this particular page has the inverse. It's essentially the square root of the inverse of the theta 2 pages ago. And this goes back to, oh, is there a universal set of notation? Unfortunately not. We need to stare it and then establish the correct intuition. So what we want to mention is how do we learn the L or the scale parameter as the hyperparameter in Gaussian processes? We have been talking about hyperparameters such as, hey, the regularization parameter, the scale parameter of Gaussian kernel if we use SVM or kernel regression. They're hyperparameters. Therefore, they are not part of the learning algorithm. But with Gaussian process, because the prediction was actually done with the whole training set, we can actually have an additional routine that learns the hyperparameter in the way that we're familiar with. There we go. Right, so the marginal likelihood of y given x and the kernel parameter, so in here we're treating the kernel parameter as part of the parameter, is a normal distribution. And the marginal likelihood, because this is a Gaussian exponential, square exponential form, we actually have the quadratic term y transpose k inverse y, and because y has 0 mean, the linear term drops out, and we're just left with two constant terms, one of which is the normalizer involving 2 pi, a number of dimensions, and the other one is involves determinant of the kernel. If we remind ourselves what multivariate Gaussian has, right? These are the normalizers in front of the multivariate Gaussian. And where is the kernel parameter hiding? It's hiding basically in this term and this determinant term. And where we're going is we would like to learn this kernel parameter using gradient descent. And how to do so is basically we look up our matrix cookbook and thank our mathematicians and to having worked this out for us for the purpose of this book. This class, you don't need to derive this yourself. Of course, feel free to convince yourself that these matrix identities and matrix differentials are actually true. So if we do gradient descent with respect to some theta, the first term involving the determinant will actually, we apply chain rule, right? So the partial derivative of log of the determinant with respect to some parameter x for a matrix is actually trace of A inverse times the partial derivative, the chain rule of the matrix with respect to the parameter, which is still a matrix. The trace of this matrix product is how we differentiate with respect to the scale parameter and other parameters. And the second term is, we know that Y is training data, so these are constant. We just need to differentiate this matrix inverse with respect to the parameter hidden inside it. And lookup matrix codebook, the chain rule says basically it's the matrix inverse itself times the differentiation of the matrix with respect to the parameter times the matrix inverse again. So this is how we implement gradient descent. With the current and modern tools such as JAX or Torch, you can simply give it the objective function and it will do this for you. Or you can expand one step, sometimes with speed ups. Remember Cholesky factorization. We remind ourselves that the matrix inverse is computed through the Cholesky factorization. Turns out that what we can do is to also do trial and error. Essentially, if there is one dimension of hyperparameter with searching through or low dimensions, we can essentially do Cholesky decomposition of the current K, compute this alpha vectors as we meant to, and then plug it into this transform form, which is depending on how we would like to do it, because computing K inverse itself requires Cholesky. And if we do this for each gradient step, that might be expensive as well. So coming back to the one of the motivating applications, right? So we're trying to learn how to move a robot arm with only 7 joints. The top block specify the problem that we wanted to solve. We use a squared exponential Gaussian covariance function, and then we use separate length scales for each input dimension. Basically, each of the 21 different input dimensions. As you can imagine, the position, velocity, and acceleration are probably with different length scales. And then we can optimize the marginal likelihood on the subset of the data to tune the choice of each of these length scales. The training data consists of 49,000 input-output pairs. And what we do is we can use about 90% of it for training and then evaluate how well it does in the remaining 10%. So you learn to remove a robot arm by essentially moving the arm jointly, like randomly. And the evaluation metric is standardized mean square error on how much the arm moves. That's different from where you expect it to move. And also mean standardized log loss, basically holdout data likelihood. So we can compare the book presents results of linear regression and Gaussian process. You can see there's about 7-fold error reduction and the improvement in likelihood. In log scale, the likelihood improved by about whole log scale, right? 1 point. So, and the 2 middle methods just did not produce the full prediction, produce full predictive distribution. But as you can see in the relatively simple real-world tasks, one of the bottlenecks is actually there are lots of training points. And this is where Cholesky factorization and also computing these inverses come from. So inverting 1,000 by 1,000 matrix that has 1,000,000 entries, you can do it in a laptop. But inverting a 45,000 by 45,000 matrix, even if we have Cholesky factorization, it will take a while, let's say, even if we have enough memory to fit this matrix on the laptop or a bigger machine. Is there any questions, or shall we go to the next poll? Gonna wait a bit and then turn on the poll on my end. The poll should be active, so go ahead and jump at it. If you have your browser ready, I'm gonna share the response screen. There we go. Okay. Okay, cool. I think the crowd is more or less converging. Right, so A is correct. One can think of Gaussian process regression as just a joint multivariate distribution. And then the correlation is induced by kernel functions we define and choose. And we can compute the predictive distribution of Gaussian process regression, which is the main focus of Gaussian processing regression on the new point X star equates to conditioning the multivariate Gaussian on all the training points. Right? And we can use the matrix inverse to compute the mean function instead of Cholesky, but it does still cost an order of n cubed, but with a larger constant as we walked through just now. And apparently everybody has been paying attention on what we said about notations and length scales. Yes, increasing S will mean actually, like if we think of it as width, it's actually being divided. It will actually make GPR varying more quickly rather than smoother. And at the end, this last one is slightly tricky, right? Yes, we can compute alpha using essentially the regularized kernel inverse times y. And it can be seen as one measure of the training data importance. But remember, there's another term. So basically, kernel of X star, comma, big X. right? So this will be multiplying alpha when we try and make prediction. So the contribution from each training point is to a particular prediction is in two parts. One part, I would say overall, this point E is kind of correct. It's still correct if we're in the exam. But if we're computing a mean of Y as a function of X star, it's influenced by two things. One is this, one is that. Okay, I hope that makes sense. Right, to recap, we revisited Bayesian linear regression, kernel regression. The BLI is faster when the number of features is much less than n, but it restricts to the functional class we assume. In Gaussian process, the prior distribution assumed to be all possible functions subjected to the kernel assumption and hyperparameters. It's quite a powerful representation. It's quite flexible as well. And the mechanism for implementing Gaussian process regression is simply this, right? What we need to choose, we still need to choose the regularization parameter and our kernels, and potentially also learn the hyperparameter of kernels. We implicitly assume that we want to work with many features, or we have at our disposal many possible features, but not too many training data points. And we don't need to worry about the lack of degree of freedom to fit all the data. The training is limited to n-cube complexity. There has been lots of work done to approximate Gaussian processes and speed up its inference. So there's chapter 8 of the GP book, and also Tang Bui, the 2024 and 2025 lecture of SML. His research agenda is on actually efficient Gaussian process inference. And here is the promise notation contrast table between the Bishop PRML book and the GP book. As you can see, the GP book adopts this notation of normal distribution of functions. I guess you see what comes from. And then in the Bishop book, it still inherits this notation that the output in training data is called target, but the function value we learn is Y. But the GP book has this X star and Y star, and moreover, F star notation to denote what we're going to estimate. Okay, that's all. Right, okay. Another question from Julian, is the mathematical theory here in this particular lecture fairly stable or still evolving? Good question. I would say the basic understanding of Gaussian processes and how to do this, is fairly established. The practice of how to choose kernels have evolved more recently, but there's also a large body of literature. The body of literature that performs efficient Gaussian process inference and also connects it and uses it in all possibly many other machine learning scenarios and combines it with different models are still evolving. I hope that answers the question. So we're at 10:44. We have about 10 minutes left. I'm going to go on the, so I'll tell you the wish list for the first half of this semester, which is, well, okay. We wish to cover Gaussian process classification, at least the main ideas. And we would also like to show you, so here's a preview of what we're gonna do next time, because there's no time to show you the full extent of it. Wait, okay, let me bring up. Yep. Okay. This files. So we'll revisit Laplace method next week and Gaussian process classification. And where we're headed is as follows. Here. Right. So today we have covered this and this. So this is done. All of these were done. The block that's left is here, and we will come here from Bayesian logistic regression. And after that, we desire to cover something else, basically latent factor models. And as you can see, there's a different cube being drawn now. And why is that? Because just also to show you that this cube, despite we've spent a lot of time here, it's certainly not the only sensible cube, right? We can draw different connections when we now assume that we have always been assuming a supervised learning setting. Basically, we observe input-output pair, X and Y, let's say, or X and T. And what we can another problem that machine learning is concerned about is unsupervised learning. Basically, we can think of it as, okay, we observe Y, let's say, and X, it's latent. We can imagine there's some latent low-dimensional X that generates, let's say X is 10 digits, 0, 1, 2, represented in some fashion to 9. And then Y are the images of written digits, right? And we could also have some really high dimensional measurement, let's say from a spacecraft or a particular chemical plant. But the key driving factor within those are actually much lower dimensional. So we could have latent Gaussian models and factor analysis. And we can do this in a probabilistic way. So this leads us to PCA and probabilistic PCA, which we will cover just before the mid-semester break. Right, and on the familiar parts of this new cube, we know linear regression, we know Gaussian process regression, Gaussian process classification, and logistic regression. So this new cube is built by essentially, let me see what's a sensible color to do this. Cutting our Zubin's cube in a diagonal, right? These 4 nodes connected together to become the new face of the new cube, and then adding latent variable to become another cube. In the interest of time, I'll just stop here for this particular lecture. And I'll pause to see if there's any further questions. If not, thanks for joining online and also getting up early to do this. So next week, I hope we'll see you guys in person. And that will be the last lecture before the semester break.